Okay, in this video I'm going to talk about electrophilic addition. Electrophilic addition happens when you have an alkene, an unsaturated hydrocarbon with a double bond between two carbons, and the double bond acts as a region of high electron density which the electrophile is attracted to. Now there are four electrophiles that you need to be familiar with. Halogens, for example bromine, hydrogen halides, for example HCl, hydrogen, and water. These can all act as electrophiles, and when they add on to the unsaturated molecule, the double bond breaks, and the two halves of the electrophile will add onto each of the two carbons on either side of the double bond. If you have a symmetrical electrophile, so for example bromine or hydrogen, it's quite straightforward. One bromine atom will go onto the carbon on the left, the other on the right, or one hydrogen, and you'll end up with a symmetrical molecule, a dibromo alkane in this case here, with the two bromines being on adjacent carbons, and this will just turn it into an alkane if you add a hydrogen to it. In the case of hydrogen halide or water, you get an asymmetric product. Hydrogen halide, you get the hydrogen adding to one of the carbons and the halogen adding to the other one to form a halogen-alkane. And in the case of water, you get a hydrogen adding to one carbon and an OH to the other carbon to form an alcohol. You do need to know the conditions for these. For halogens and hydrogen halides, the reactions are spontaneous. They don't need any special conditions for this to happen. For hydrogen, you require a nickel catalyst and heat. And for water, you require a strong acid catalyst, so either sulfuric acid or phosphoric acid, and heat. Note that this reaction with water is a reversible reaction, and therefore the pressure is going to be the deciding factor as to which way the equilibrium will shift. Under high pressure, you'll tend to shift to the products with the alcohol, and at low pressure, you'll tend to shift back to the reagents with the alkene and the water. The heat is such that everything is gaseous. So the mechanism which is required for the higher levels for the electrophilic addition, and you also need to be able to know, to be able to predict the products when you have an asymmetric alkene and asymmetric electrophile. So the mechanism that we have here, you have your nucleophile, so I'm going to use hydrogen HCl for this. If you've got HCl, this molecule is polar, so you've got a delta positive hydrogen and a delta negative chlorine. Now the hydrogen is going to be the electrophile on this molecule. The hydrogen is going to be attracted towards the region of electron density in the double bond, and it's going to attract electrons from that bond towards it. And a pair of electrons from the pi bond of the double bond will be attracted towards the hydrogen and will break this bond here and will form a new bond with the hydrogen. So what you end up with is a molecule, or an intermediate rather, that looks like this. So the hydrogen is now bonded to that carbon. This bond between the hydrogen and the other half of the molecule breaks, in this case between the hydrogen and the chlorine breaks, so the chlorine ends up as a chloride ion, negative ion, with a lone pair of electrons on it. And the other carbon, which was part of the double bond, which has now got only 3 bonds, ends up as a carbocation. So we have a carbocation here because this has lost both of these electrons towards this bond, and the halide ion because it has gained both of the electrons from this bond. So the intermediate that we form here with the carbocation will then react with the other half of the electrophile, in this case the halide ion, the chloride ion, and the electrons there will move towards the carbocation to form the product. So we've got the hydrogen on there, and the chlorine is now attached to the other carbon. So that's if you're using HCl. If you're using water, you'd see something very similar happen, where you'd have the hydrogen bonding onto one of the first carbon, and then the OH would then attract onto the carbocation. So that's the mechanism. To predict the products of an asymmetric alkene with an asymmetric electrophile, we can use propene as an example. So propene has a double bond between two carbons, and then on one of those carbons we have a CH3 group. And if we use again our hydrogen chloride as our electrophile, this is also asymmetric. Now there are effectively two choices. There are two ways that this can work, because the bond can either break with the new bond forming from the left-hand carbon or the right-hand carbon of the double bond. So you can end up with this intermediate or this intermediate. So here, the carbocation, so in this first one, the carbocation is now on the central carbon, and on this option here, the carbocation is on the leftmost carbon. And it just depends which way this double bond has broken and which of those carbon atoms is becoming the carbocation. This choice is not random. If it was, you get a 50-50 mixture of both, and you get a 50-50 mixture of products with one chloropropane or two chloropropane as your products, because this one here is going to end up with the chlorine on the central carbon, and this one here is going to end up with the chlorine on the left-hand carbon. So this one is 2 chloro, and this one is 1 chloro. Propane. So if it was random, it would be a 50-50 mixture in terms of the products. However, this is not what we see. What we see is disproportionately you will get 2 chloropropane out of this. And the reason for this is because of the position of the carbocation in the intermediate. Having the carbocation in the center of the molecule here is much more stable than having it at the end of the molecule. And the reason why is because these neighboring CH3 groups, the one that was already there and the one we formed, they're able to stabilize the carbocation due to the electron inductive effect. So in this variant here with the carbocation on the central one, there are 2 methyl groups which are able to shift electrons towards that carbocation, stabilizing it. In this option here, there is only 1 carbon adjacent to the carbocation to stabilize it, so it's far less stable. And therefore, you will always end up with a product where the carbocation formed on the carbon which had the most carbon groups around it, which generally means towards the center of the molecule. You do not tend to get the carbocation forming on the end carbon of a chain if that's one of the options. Obviously, you don't see any difference if you're using a symmetric electrophile, for example, bromine or hydrogen, because the products would be symmetrical anyway. It doesn't make any difference. And if you have a symmetrical alkene, so for example, if you've got but2ene with the double bond in the center of a chain of 4, then it doesn't actually make any difference either, because the end product will be symmetrical as well. But you see an effect where you have both an asymmetric electrophile and an asymmetric alkene.